All right, girls, so now that you've seen the applications of the second derivative with one polynomial function, I want to take you through one more example. I'll also give you an example of an equation that involves a fractional exponent and one that involves a trig function. Now, I would recommend maybe continuing the videos until you feel comfortable and then going on to your homework, or if you want to start homework problems and then come back to the videos to help you along, whatever process is most comfortable for you. So here I'm given a quartic function instead of a cubic function like we were given in the previous problems. So instead of using the first derivative to find the extrema, let's go ahead and use the first derivative just to find our critical points. And then once we have our critical points, let's find our extrema with the second derivative test. So here, if I take the derivative of this function, my first derivative, if this is just a polynomial function, is going to be negative 4x cubed plus 8x. And then to find my critical points, I'm just going to set that equal to 0. Then the easiest way to solve this guy is going to be to factor out a negative 4x, and that's going to leave me with an x squared minus 2. So then I have two terms that I want to set equal to 0. I have negative 4x is equal to 0, and I have x squared minus 2 is equal to 0. So then I want to solve for my critical points. Divide by negative 4, divide by negative 4, and x is equal to 0. That's one of my critical points. And then I have x squared is equal to 2, so my x values are equal to plus or minus root 2. So I have 3 critical points. And now I can find the extrema of my critical points using the second derivative test. So on tonight's homework, if you're asked to find extrema using the second derivative test, this is the process that you want to follow. So I found my derivative here. So let's go ahead and find our second derivative of that same function. That second derivative will be negative 12x squared plus 8. And so now what I want to do is to go ahead and plug in each of these 3 critical points into my second derivative and use that information to make conclusions about my extrema. So let's plug in our smallest critical point first, which will be the negative square root of 2. So if I plug that in, I have negative 12 times negative root 2 squared plus 8. And that's just going to give me 2, if I square negative root 2, times negative 12, so negative 24, plus 8 is going to give me negative 16. Now this is less than 0. So what that means is at negative root 2, I have a relative max. Then I want to go ahead and plug in 0 as my critical point to my second derivative, which is negative 12 times 0 squared plus 8, so that's positive 8. That's greater than 0. So using the second derivative test, that means I have a relative minimum at x equals 0. And then I want to evaluate my positive root 2. And this is going to give me the same answer as plugging in negative root 2 because I'm squaring the value. So I'll get negative 16, which again is less than 0. So at root 2, I also have a relative max. So if you're asked only to find extrema using the second derivative test, this is where you would stop, but I would go ahead and take those points and plug them back into your original expression up here. So if I were to plug in negative root 2, I'd have negative root 2 to the 4th, the negative out in front, plus 4 times negative root 2 squared. And if you do that in your head or plug into your calculator, you'll get out 4. You get the same answer as if you plugged in positive root 2 because I have even numbered exponents here. So that means I have a relative max that's happening at negative root 2 comma 4 and also at root 2 comma 4. Then if I wanted to plug in 0 to figure out the y value of my relative min, this one's easy because my x's will take me to 0. So my relative min is happening at 0, 0. So that's how we use the second derivative to identify our extrema. Then what we also want to be able to do is to find our inflection points. And remember, the inflection points are where your graph has its steepest slope, so where it's most rapidly increasing or most rapidly decreasing, and it's also going to be the value where you change concavity. So let's go ahead and find our inflection points. And remember, we're just going to take our second derivative here. So we are going to take negative 12x squared plus 8, and we want to set that equal to 0. So I'm going to have negative 12x squared is equal to negative 8 by subtracting that over, divide by negative 12, divide by negative 12, and I'm going to work horizontally here. So I'm going to have x squared is equal to, if I simplify that, my negatives divide out and I can divide both terms by 4. So I'll have x squared equals 2/3, square root both sides, and that means I'm going to have inflection points at plus and minus root 2/3. So those are my inflection points. That's where my graph is changing its slope most rapidly, and again where the concavity changes. So it's also a good idea to figure out what your y values would be if you plugged them back into your original function, just to know what those actual ordered pair points are for the inflection points. So let's just figure that out too. So if we have f of root 2/3, I'm sorry, that's my dog barking in the background, we'll have negative, and we've got root 2/3 to the 4th plus 4 times root 2/3 squared. So let's go ahead and plug that into our calculators together. So if we have root 2 divided by 3, raise that to the 4th, make it negative, and then add 4 times the square root of 2 divided by 3, that quantity squared. And if we make that a fraction, we should get 20/9 if you plug that into your calculator. Now those values are going to be the same for positive and negative root 2/3 because again my exponents are even. So that's where my y value of my inflection point occurs. So next up, we want to use the inflection points to determine intervals of concavity. So again, this is just where we're doing testing points. So I have two inflection points, so I want to check on either side and in between those inflection points. So I want to check x less than negative root 2/3. I want to check in between negative root 2/3 and positive root 2/3. And I want to check x greater than root 2/3. Now, kind of the nice thing here is that we've already tested points in those intervals when we tested our critical points with the extrema. So notice how negative root 2 here, if we were to plug that into our calculator, negative root 2 is negative 1.41. If we were to plug in negative root 2/3, that's negative 0.816. So that value of a test point of negative root 2 is just fine to use here. Our critical point of 0 is fine to use here. And our critical point of root 2 is just fine to use here. So what that means is when I plugged this in to my expression up here, I got out negative 16, which is negative. When I plugged in 0, I got out 8, which is positive. When I plugged in root 2, I got out negative 16, which is negative. So that negative means I'm concave down over that interval. And then in between negative root 2/3 and positive root 2/3, I am concave up. And then greater than root 2/3, I am concave down. So this is the extent of what your homework will ask you to do tonight. It will either ask you to find extrema with your second derivative, it will ask you to find inflection points, or it will ask you to find intervals of concavity, but they're all connected. And we could use this information to make a general sketch of that original polynomial function we were given. You won't have to do that on your homework tonight, but let's just see what that would look like. So I'm going to go ahead and make an XY graph here. And let's just plot this information out. All right, so I first found my extrema, right? And I found that I have a relative min at 0, 0, and two relative maxes at negative root 2, 4 and root 2, 4. So let's go ahead and plot those points. 0, 0 is my min here. Root 2 is kind of right around 1.2, so we'll kind of go right here, and then up 4. Let's make this 4 on our y-axis. Same thing to the left, at negative root 2, I'm also up at 4. So I have relative max, relative min, relative max. And then I also have my critical points at root 2/3 and 29ths. So let's get an approximation there. 29ths is about 2.2. So let's go to negative root 2/3 right around here. And then 2.2 is going to be right about here. Same thing, plus root 2/3, and then my y value is 29ths, so right around here. So everything to the left here is going to be concave down. In between here is concave up, and then I have concave down again. So my graph is increasing up until I hit my relative max here. Then it decreases downwards to my relative min. Then it comes back up and hits my next relative max. And then it decreases downwards. So this is the general sketch of my polynomial function without having graphed it. And so we can see here on the left of my inflection point, my graph is concave down, just like we predicted. In between my two inflection points, it's concave up, and then to the right here is concave down again. And you can see at those inflection points, that's where your slope is the steepest. So that's all of the information we can get from our first and second derivative tests combined.